In this video, we're going to talk a little bit about an introduction to the concept of something called vector quantities. So let's actually start this off with a title, vectors versus scalars. So there are two categories in which we can place every type of quantity. We've actually already looked at one other type of categorizations where we talked about the fundamental quantities and the derived quantities. So every quantity is one of those two, based on its units. But vectors versus scalars, there's a different distinction between these two types of quantities that are distinguishing. So the way that people tend to define these is that scalar quantities are quantities without any inherent directionality, and that vector quantities are quantities with inherent directionality or magnitude and direction, where magnitude just means the size of. In fact, I'm just going to write that down right now. Magnitude, you might know that word from like the magnitude of an earthquake, which means the size or strength of the earthquake. So magnitude just means the size of the quantity. I'm going to define vectors and scalars slightly differently, and I think it is a meaningful distinction rather than what we were saying before. And the key aspect here is that a scalar is a quantity that is not affected by directionality when mathematical operations are performed with or on it. A little clunky as a definition there. Kind of invert this a little bit when we're talking about vectors, because a vector is a quantity whose directionality affects the outcomes of mathematical operations performed on or with that quantity. A lot of people just like to talk about, well, vectors are those things where direction matters. But I want to just be a little bit more explicit, like why does it matter? It matters because when we use vector quantities with other types of quantities, the direction of that vector affects the math that you do with it. Otherwise, if there's no real change that occurs to it, why would we even care about it? So with that being our definition, what we're going to do is we're going to list different types of quantities that are vectors and scalars. So what I want you to do is stop the video for a second and brainstorm a list of quantities that you think are vectors and you think are scalars. A good place to go is to our list of fundamental and derived quantities, just so you can get a list of quantities that you can talk about. So stop the video, think about that for a second. Hopefully you actually did stop the video and think about that for a second, but I'm going to start listing some things out here. So mass is a vector, right? Because it would make no sense to say something like, well, if I had 8 kilograms and 4 kilograms, I have 12 kilograms. It's not like I have 8 kilograms to the right and 4 kilograms to the left. That just doesn't make any sense in terms of what that quantity is about. So another scalar quantity is time, right? Time that, I'll be perfectly blunt. How about this? Time is a scalar quantity prior to about 1905. Once you start getting into Einstein and stuff like that, there's some argument that can be made about the arrow of time, but we're not going to get into that. That's well beyond the scope of this course. Some other scalar quantities, distance. Now, that's a fairly controversial one because people are like, well, distance, so I could travel 3 meters to the left. And I would say, well, you're right, you can, but you have just described a quantity that is not distance. There is a different word that means a quantity in a direction in terms of length, and that is going to be the word displacement. And we're going to get back to that when we talk about motion, and we'll define that idea of what is displacement a little bit later. So distance is a scalar. 3 meters, 4 meters, 5 meters, 6 meters, those are distances. I can put lengths in there, and I'm not going to go into all of that. So like distance, length, height, width, depth, all of those things are scalar quantities. Area is a scalar quantity. Volume is a scalar quantity. I will say in higher order physics, we have ways of turning both of those things into vectors, but once again, way outside the scope of our course. Some others, speed is a scalar. Now you might be saying, hold on a second, but I can go 4 miles an hour east. I go, yeah, you can go 4 miles an hour east, but what you've described there is velocity and not speed. So speed and velocity are not the same thing. When we get to our motion unit, we'll see that their definitions, although similar, are not the same, right? So speed as a scalar quantity. So if we're kind of getting the notion here that we have many more scalars than vectors. So in the same way that we said with derived quantities versus fundamental quantities, if you know all the fundamentals, those things that are not on it are the derived. It's going to be kind of the same thing that if you know the vectors. And I will say every time we encounter a new quantity, we're going to see which list that it lands on. So there won't be very many mysteries there. Some other things that we're going to talk about that are going to be vectors, just to add some there, the concept of acceleration is going to be a vector, as well as the concept of force. That's going to be a very important vector because the direction I push matters. Because if you have two people pushing on something, it really matters how they're pushing to see the resulting outcome of both of them pushing on that device. If they're both pushing on the same side of a box, you get a very different outcome than if we're pushing in opposite ways on the same box. So since the combination of those forces and the directions that those forces act affect the outcome of the combination, that's how it falls into the vector definition. Another physics word that you may have heard, but I'm just going to throw it on our list for now. Momentum. Not that you might know what that is, but I'm going to say it's on the vector list. Maybe another scalar quantity to throw on here: speed, area, volume, time, distance, length, mass. A very important one, energy. Energy is a scalar, and that's going to become really important to us later on. I'm just going to throw one more onto the vector list. Current. When we get up to talking about electricity later in the year, it's going to be important that the flow of that current matters. The reason why I put that there is I do want to talk about another scalar quantity, which is charge. And a lot of people have a problem with that as being a scalar quantity, because if you remember for chemistry, we have both positive and negative charges. But that positive and negative, which we often think about on a number line, right? That's not what that means with respect to charge. That positive and negative are about an absence of something or an excess of something. So we'll get back to that, but for now, we're just going to put it on our list as something to know that charge is a scalar quantity. So this is not the complete list in all of physics, but these 5 are going to get us through pretty much the first semester and a half, and then we'll see some new quantities that may end up adding onto this list. And we'll definitely see more that add up onto this list, but this is a good starting point. So vectors versus scalars. So why do we care about those things? Well, we care about those things very specifically because we perform mathematical operations on quantities all the time. Very specifically, addition is a very popular thing that we're going to perform. And the way that vectors add is very different than the way that scalars add, okay? So my classic example on this is just a simple thought exercise. If I have 3 plus 5, what is that going to equal? All right, stop the video, think about it for a second. Well, obviously, I'm pretty sure that most people just automatically and impulsively said 8, that 8 is always the answer to that. And I would say, well, in pure mathematics, maybe, but not in the realm of physics, not in the realm of science, because we would never have a statement like this anywhere down in any physics problem, because there are no units. These are not quantities. They're just abstract pure numbers, and physics doesn't deal in the realm of abstract pure numbers. We deal in the realm of quantities. So can you think of a quantity that I can put such that 3 plus 5 is always 8? And if you said grams, you'd be true. 3 grams plus 5 grams is always 8 grams. 3 seconds plus 5 seconds is always 8 seconds, right? Notice that grams were a unit of mass and seconds was a unit of time. So if I add two like scalar quantities, I always get just like normal addition, normal subtraction processes going on here, because that's the way that scalar addition works, okay? But if I were to say 3 meters plus 5 meters is 8 meters always, well, that's not necessarily true. Now you say, but hold on, that doesn't make any sense. If I walk 3 meters and I walk 5 meters, I have always walked 8 meters. And to that I would say yes, because what you've described is what total distance did you travel? I traveled 3 meters, then I traveled 5 meters. But if I traveled 3 meters east and 5 meters west, I would actually get the answer of 2 meters, but 2 meters west, right? I could actually go 3 meters east and 5 meters east and get 8 meters. That's a possibility. But I could also go 3 meters east and 5 meters north. And if I asked you the question, how far are you from where you started? That answer is not 2. That answer is not 5. That answer is, what is it? Hopefully you're thinking radical 34 meters. Not that we should know what radical 34 meters is, but just throwing that in my calculator for half a second here, right? That's 5.83 meters. That's how far I am from where I started. So that is an acceptable answer for this problem, right? Because the direction of these quantities mattered in terms of the mathematical outcome. And that's what I'm talking about with vectors. So what we're going to be building up to now is talking about vector addition. But there's one other background basic vector skill that I want to talk about before we go on to the next video, which will talk about the concept of vector addition. And that is how to graphically represent vectors. And for this, you're going to follow along. You will need yourself a straight edge with a centimeter scale. And I'm going to use my protractor here because eventually we're going to need that. Now, I'm just going to pause for a second and say, the way that I define vectors, I probably should have said this in the beginning. If you were to talk to a mathematician or a computer scientist, they might have different, more abstract definitions of vectors that are probably more appropriate if we're talking in the realm of pure math. I'm not claiming that the definitions that I offered are the correct definitions, but I'm going to say within my profession, within our constraint of in the realm of physics, these are workable, functioning definitions that really tell you the heart of the thing. And that's something subtle but true that we need to always think to ourselves. Is this definition that we're given like the quote unquote true definition, or is this something that we're saying in this context, we're going to take as true because this is the most meaningful and functional definition for understanding and communication within the field? That happens all the time. Okay. Anyway, how to graphically represent vectors. Let's say I had some arbitrary vector A. So let's get some notation down. A. I don't know, just like to have a variable for it. Now, if I want to say this is a vector quantity, I would put a little hat on top of it, right? Little half arrow. Now, that half arrow doesn't point in any direction. It's always going to be shown to the right. So if the vector is a vector to the left or up, out, in, down, east, west, north, south, whatever, to the left, to the right, northeast, we don't change the direction of that. This just reads as vector A. Okay, vector quantity A. So let's say vector quantity A is 5 meters, and we'll just say, I don't know, east. Okay, so what we have here is a vector quantity that has both the size of the measurement, right, an indication of the type of measurement it is, because meters, and then the direction. Okay, so couple of other notation things here. Remember I said before I defined the word magnitude, which was the size of the measurement. So in this case, what is the magnitude of vector A? If I looked at that, oh, well, irrespective of the direction, this measurement is 5 meters long. So we need to have a notation for that. So here we go. If I put a hard bracket around, or sorry, not a hard bracket, that's our, if I put a hard bracket around that, we know that that would be meters because the units of A are meters, right? So what I want to do here is technically the way we say the magnitude of is a double bar around the vector quantity. So this would say 5 meters. So the measurement of A is 5 meters. Now, that looks very much like another symbol that you know. And that symbol that you may be thinking of is absolute value. And there's a lot of connections between the concept of absolute value as well as the concept of magnitude. So let me just write this as a sentence. The magnitude of vector A is 5 meters. If you think about what absolute value means, so if I have 7, right, absolute value of 7 is 7. Absolute value of -7 is 7. So absolute value is in a line, in a linear sense, right? How far along the number line is that quantity from 0? And if you think about what magnitude is, that's going to be kind of similar if we are kind of thinking of this thing in terms of lengths. But magnitude is going to capture so much more because it's just saying, absent the directionality, how far is this thing from the origin? But we're no longer going to be trapped to one dimension on that calculation. So functionally, it looks like those two things are the same, but there is a subtle difference. So you can think of magnitude as sort of like a higher order, a higher dimensionality notion of absolute value. That being said, that is why, for laziness sake, you will often find in many textbooks or online that they'll just use a single bar to mean magnitude in the concept of physics. And mostly that's just because getting this symbol is just typographically harder. So we're going to use these two things interchangeably. But I will tell you in this course, please do not read that as the absolute value of vector A is 5 meters. Please say the magnitude of vector A is 5 meters, right? So it's a poorer notation, but we're just going to roll with it. Okay, great. So that's the notion of magnitude. Now, what I want to do is graphically represent that. So in order to graphically represent that, what would we do? Well, you may say, oh, I'm going to draw an arrow. Yeah, but there's a couple of problems. So if you were sitting in your house right now or in school, point east, right? Do you even know which direction is east? Well, for most people, think of what direction compared to where you are is White Plains. And for me, that's that way, right? And so therefore, White Plains is to the north of me. So the east is that way. So that's east for me. But if I tried to draw that on my paper, it would be insane. So the first step in graphically representing vectors is going to be to impose a coordinate system onto the page. That way it gives meaning to the directionality, and we can be clever with this to make our lives easier. Now, there are two general coordinate systems that we will see in this class. The first is the XY coordinate system. I know we were talked earlier about not X, not Y, but we really do mean XY in terms of the XY Cartesian coordinate system, right? Our normal coordinates that we're used to, horizontal and a vertical axis, that Descartes called the X and Y axis pretty randomly, but that's what that is. And the other is going to be the compass rose. And you may have seen that on some maps and whatnot. It's just a little thing off in the corner where we label a north, an east, a south, and a west. So now I've imposed a coordinate system onto this page. Now, the nice thing about that is, remember we said the problem point east in life, I don't care. East on this page is to the right of the page. Notice here, even if I rotate my page to do work, the meaning of east hasn't changed. It's not to the right of the page, it's to this side of the page. And once that's imposed onto the page, that's our truth for this thing. That's our declaration. And we're allowed to do those declarations as long as we communicate effectively what those declarations are to the reader, right? And that's sort of like the power of notation, right? An agreed upon notation is an ability to be clever with it, yet it still be understandable to multiple people. All right, so that's our first step, impose the coordinate system onto the page. The second thing that we're going to need is, so now I know what direction is east. So I've captured a lot of the information on the page. The second thing we're going to need is a scale, right? Because we know we're going to draw an arrow to show directionality. I'm going to give this a different name there in a second. But scale, we want to know, well, how long of an arrow are we going to draw? So here, I think a nice scale to use is 1 centimeter is equal to 1 meter. So we're always going to say a centimeter is equal to something, right? And so how big should our scale be? So rule of thumb on scale. We tend to want to not have our vectors be smaller than about 2 centimeters long. And we want to make sure that we scale all our vectors so that they all fit on the page. So which of those is the more important constraint? I think it's clearly the vectors have to fit on the page, right? So if fitting our largest vector on the page forces the smallest vector to be smaller than 2 centimeters, that's fine. But we generally want to maximize the length of our vectors with respect to the page so that our smallest vectors are long. Well, why do we want that? Well, folks, you're going to be using a tool, and that tool has an absolute error, right? And so let's say we have something that's smaller than 2 centimeters, smaller than 2 centimeters. This tool goes down to the millimeter, right? And so if I have something that's smaller than 2 centimeters, I'm already talking about like a 5% relative error with that thing at the least. And we want to minimize our relative error. So because there's some estimation, and then we have like, the width of your pen, probably even the absolute error of this is not the thing that's going to drive the error, but really the width of the ballpoint or the width of your pencil is going to be the thing that's driving the error in that case. So in order to minimize the significance of that error, see, common themes come around. That's why we want all of our vectors to be 2 centimeters or longer. Okay, so next, I got to start drawing it. Well, if you notice here, the vector just says 5 meters east. What does the vector not tell us? Well, very clearly from its absence, the vector does not tell us a starting point. And that's going to be so critical in terms of our spatial understanding of vectors and our ability to manipulate them. So what we need to do is pick a logical starting point. And that logical starting point can be any point, since the vector does not specify its starting point. And I'm going to write that down. Since vector quantities do not specify a starting point. We're going to make use of that later. But in the same way that we said that some arbitrary measurement or arbitrary standards for measurement were better than other arbitrary standards for measurements, just the same thing. Some starting points are better than other starting points. I wouldn't want to pick a starting point here. Why? It's in the middle of text that I've written. Let's not do that, folks. Let's pick or rather, let's draw our pictures so they are not in the middle of our text. We have all this blank paper that we can use. Let's let it live on itself. Also, we don't want to pick something over here on the side, right? Because it's going to run off the page. So you have to think about what are all the pieces of information I know to pick a legitimate starting point. So when I do, here we go. I'm going to go into a blank page. I'm going to pick something reasonably in the center. There you go. If you have lines on your page, that sort of probably makes it easy. What I'm going to do here is I'm using the side of the page right here, and I have a marking at the 0 point, and I'm making sure that marking for the 0 point runs along the side of the page. Therefore, I know that this line here now is perpendicular to the side of the page. That I don't know, that's just maybe my compulsion of wanting everything to be perpendicular and parallel, but there it is. And you'll note there, what I did is I just drew a little guideline at my start point, right? So pick a logical start point, and I'm going to recommend a horizontal guideline through the start point. And you may say, well, why do I need that? Well, as things get more complicated, we're going to see that that's going to be really helpful. Okay. Great. So the next thing I'm going to do is I'm just going to draw a ray or arrow to scale, but we are going to call it a ray. So here we go. And being that my vector is 5 meters, that is 5 centimeters. So here you go. 1, 2, 3, 4, 5. Boom. And I'm going to put an arrowhead on the end of it. Okay. Now, I know there's some people out there just screaming at me, and you're saying, but Mr. Fon, a ray goes on infinitely. Yeah, as a mathematical figure, it does, I guess. But in physics, we use rays to represent vectors, and we will scale the drawn size of those rays to the size of the measurement when we are doing scale drawings. And you're just going to have to live with that dichotomy. Okay, cool. The last thing we want to do is label the vector. All right. And the way we're going to label it is with its name, which is a vector. I'm not going to label with the 5 meters. We don't want to tend to put too many numbers on our diagram for reasons that we will get to when we get into the physics of it, right? So there we go. Everyone see? Okay, great. So I'm going to draw something else now. I'm going to pick a new starting point. Everyone see that? And I'm going to go. We're going to see how long that is. Okay. So what did I just draw? Well, it points east in the same way that this vector pointed. And if you saw the length of it when I was drawing it out, it's 5 centimeters long. So this is a 5 centimeter long, therefore 5 meter long vector that points east. Oh, you know what that is? That's vector A. So what I did is I just drew another one of them, but it's almost like I picked up the first vector and I plopped it down there. So I want you to think back to your early math career, high school math career. What is the name of the operation where you pick up a geometric figure and you shift it to another location without rotating it or without changing its size, formerly known as dilation? And if you remember, that is called a translation. And vectors can be translated without changing their identity. And why is that? That's because a vector quantity does not tell you its starting point. Okay? And that's going to become important when we go on to vector addition in the next video. So stay tuned for that. Ah.